So with section 4 and with section 5, we actually do some applications here with our number of moles, all right? So the number of moles at first is kind of an abstract concept. And so what we do here is this. We kind of have some more realistic things that actually happen. And so we start with percent composition because it really helps us determine, or really helps us go through and find out some useful quantities. Percent composition is more or less the grade you get on a test, right? If I had a 100-point test and you earned 83 points out of the possible 100, you put it in your calculator and you say 83 divided by 100, and then you times or multiply by 100 to see your actual percent. Same thing happens here with a chemical compound, all right? We want to know what is the percent by mass of each and every element in that entire substance, okay? Questions? Does anybody need this? All right, so to go through these steps, first thing you got to do is get the molar mass. Now, I'm going to give it to you. I don't have it listed on your slides, but I will highlight that. Again, for the test, you already know how to do the molar mass. It's going to be one of those questions there that you're going to have to find the molar mass of some compound. So I'm going to know you know how to do it. Here, you got to be able to use this. What you're going to do from there is you're going to look at the specific mass or the specific element and find its total mass contributed. So very similar to finding the molar mass. Once you do that, you're going to divide it by the total compound mass or molar mass, and then multiply by 100 to get it into percent. Okay? Now, again, usually on these problems, I'm going to specify. I'm going to say, okay, I want to know the mass percent of this specific element. On the example, just to show you some more items, we're going to find the mass percent for every single element. All right? Questions? Does anybody need this still? All right, so going through this particular example, what's highlighted in yellow is not on your particular slide of notes, but the molar mass for sodium hydrogen carbonate, formula here, is 84.01 grams per mole. Each total mass for the entire compound. Now, what we need to do, typically you would say, hey, tell me the mass percent of one specific element, for example, carbon. But in this case, it does not. It says determine the percent by mass of, should say, every single element in this compound. So what we're going to do is we're going to list out every single element, just like we've done to find the molar mass, and we're going to go through this. Now, I'm going to list it in different colors just to make it easier to see here. So we have Na for sodium. We are going to have our hydrogen for, or an H for hydrogen. We're going to have our C for carbon. And we're going to have our O for our oxygen. And what we're going to do, just like we found the molar mass, we're going to look up each of these elements individually, and we are going to find out the total mass from each and every element. So you look on the periodic table. On the periodic table, you would find the molar mass of sodium Na is 22.99 grams per mole. We have to multiply this by our amount of Na in our formula. And so we say times, and I ask you this, how many NAs do we have in our formula? Just one. So technically it'd be times 1 mole, which gives us a value of 22.99 grams. And then what we do is we're going to divide it by that listed molar mass. So I'm going to go ahead and I'm going to say, okay, let's divide it by 84.01 grams. And then to follow that formula, we're going to say times 100. Okay, so when I do this, if I take 22.99 divided by 84.01, I press enter, I get 0.273, number keeps going out. I say times 100, and I round to the nearest decimal. We get this. We get 27.4% of the element's mass is Na for sodium. Okay? Questions before we move to the next element? We're going to do the same or similar thing. The only difference is this. Hydrogen has a different molar mass. Molar mass of 1.008 grams per mole times, how many hydrogens do we have in the formula? 1. So we say times 1 mole. Well, that gives us 1.008 grams. We're still going to divide it by the total molar mass again, so that 84 number. So we say divided by 84.01 grams. And because we want to express this as a percent, we're going to multiply it by 100. So we take 1.008 divided by 84.01. We multiply that by 100. And rounding to one decimal, I get 1.2% of the entire compound's mass is hydrogen. Okay, moving on to carbon. Carbon, another element here, has the molar mass of 12.01 grams per mole. We multiply it by how many carbons? 1. And so we still get 12.01 grams. We're going to divide it by the molar mass, which is still 84.01 grams of the entire compound. And we want to express this as a percent. So at the end, we multiply by 100. So 12.01 divided by 84.01 times 100. Expressing it to one decimal, we end up with 14.3% of the compound's mass is of carbon. Okay. Now, last part here, we do the same exact thing, but be careful here with oxygen. It's going to have a molar mass of 16.00 grams per mole. We need to multiply it by, very good. We need to multiply it by 3 because that's what our formula says. So if we take 16 times 3, we get a value of what? 48. Yep, exactly 48. I'm going to call that 48.00 grams, all divided by the molar mass of the compound. And we multiply this by 100. And so we get 48 divided by 84.01. And we multiply this number by 100, and I get 57.1% of this compound's mass is from oxygen. Now, I'm not going to do this, but if you add all these numbers, all these percentage is up, you will get to 100%. So it counts for all things or all items in here. Questions? Anybody need this? All right. Think of this as getting your grade on a test, how you would find your percent on an exam. Questions? Anybody need it? All right. So let's get to a useful item here that's a little bit of an extension. So when we do chemical analysis, real world chemical analysis, they don't tell you, hey, we dug this sample out of the ground and that's this sample or this substance. What happens is this. That first picture on this section of notes was what we call the gas chromatography mass spectrometer. And it's a really expensive machine, but it just analyzes and tells us the percent of each element in that particular substance that you analyze. It doesn't say, hey, this is this formula. You got to do a little bit more work to determine that. And so this is where empirical and molecular formulas come into play. So empirical formulas, simplest whole number ratio. When I think of empirical, I think of an empire, right? That is the single simplest form that this can exist in. Meaning, if you can reduce the subscripts, go ahead and reduce them, because this needs to be in that simplest whole number form. Questions? Does anybody need this? Okay, molecular formula, I think of multiple, all right? So molecular formula takes the empirical formula and it will multiply it by a particular quantity, a whole number, and it will be a ratio, okay? So for example, if the empirical formula is C3H4, you cannot reduce C3H4. And I say, all right, the molecular formula is 3 times the amount. You would say, well, our formula is C9H12 for our molecular formula. Okay, actual number. In this case, sometimes you would look at that and say, under normal circumstances, I would reduce those subscripts. Questions? Anybody want it? Need it? Okay, here we go. What we can do with this. So, if you put yourself in the shoes of a chemist in the chemistry lab there, you get this mass percent. You got to make sense of it. So here's the steps that can help us produce the formula. And they seem like a lot of steps, and I will say there's a few odd steps here. But big thing is this. You're going to get given the percent automatically. Don't even write down percent. Cross that percent out and make it grams. Why we make it grams is we're assuming we have a 100-gram sample. Then we take the grams and we go to moles of each individual element. Once we're into the number of moles, step 3 is a little bit weird. We got to look at the number of moles and we ask ourselves, okay, which of these numbers is the smallest? We divide every single one of those moles by that smallest number. Okay? From there, we look and we say, okay, if once we divide, they're still not in a whole number form, we have to make it a whole number by multiplying it by some number. All right? And just like in algebra, what you do to one side of the equation, you're going to have to do to everything else. So if we multiply everything by 3, every element gets multiplied by 3. Okay? If we're finding the empirical formula, we would stop there and we'd write down the formula. Molecular formula, we're going to have to go one step further. We're going to have to find the molar mass. We're going to have to divide it by a given molar mass, and we should get pretty close to a whole number ratio. That whole number is what we have to multiply the empirical formula by. So a lot of steps, kind of confusing to write them down, but major thing here is this. Make sure, again, the biggest thing is finding that empirical formula by doing some items that we've already covered earlier in this chapter. So any questions? Does anybody need this? All right, so here we go. All right, we have methyl acetate. We don't know what the formula is because it doesn't tell us. We want to determine the empirical formula of methyl acetate, which has the following percent by mass: 48.64% carbon, 8.16% hydrogen, and 43.2% oxygen. All right. First thing that I do in this specific problem is I go ahead and I say, hey, I do not want to deal with percent, and I'm going to make everything G4 grams. Okay. Now, what I do is this. I'm going to go ahead and I'm going to write down those number of grams in that substance. So I'm going to have, to start out with, 48.64 grams. So 48.64 grams of carbon. Then I'm going to give a little space here, and I'm going to have 8.16 grams of hydrogen. A little bit more space here, and I am going to have 43.2 grams of oxygen. Okay. Now, what I need to do is I need to get each of these substances into moles. All right. So what you're going to do, and I'm going to take this one element at a time. I'm going to say times, draw my line, and here's a question for you. What unit has to cancel down and diagonal here? Grams of carbon. Now, I've said this all along. If you're not in the middle, man, you got to get there first. So we're actually going to go to moles specifically of carbon. Now, if you look on the periodic table of elements, carbon has a molar mass of 12.01 grams to 1 mole. So right now, I'm going to pause and I'm going to perform this calculation here. We are going to have 48.64 divided by 12.01. And to 2 decimals here, I get a value of 4.05 moles carbon. Then we're going to do a similar thing for hydrogen. So we say times, draw our line, grams of hydrogen has to cancel down and diagonal. On top, we go to moles of hydrogen. We look up the molar mass of hydrogen. We find it to be 1.008 grams to 1 mole. So I'm going to pause and do this calculation. 8.16 divided by 1.008. And to 2 decimals here, this will round to 8.10 moles of our hydrogen. Last part here, oxygen. We say times, we draw our line. Grams of O, oxygen cancels. We go to moles oxygen. We're going to get really familiar with this. Molar mass is 16.00 grams to 1 mole. Okay. If we do this in our calculator, 43.2 divided by 16.00, we get exactly 2.7 moles of oxygen. At this point, this is a really odd and weird step. So if we have these numbers on our right, which one of these numbers all the way here on our right is the smallest? 2.7. Yep, oxygen, which has a value of 2.7. So I'm going to use a different color here. Everything on the right-hand side is going to get divided by that smallest number. And so what I do is this. You don't need to put moles with this, but you just need to put 2.7. And so what's going to happen is this. When I divide by our smallest number of moles, going from top to bottom, 4.05 divided by 2.7, I get a value up top here of 1.5 moles of carbon. If I take 8.1 divided by 2.7, I get exactly 3 moles of hydrogen. And 2.7 divided by itself would become 1. Okay. Now, we have the numbers on our right, now in green. I ask you this. Are these in whole number form? Not all of them. 1.5 is definitely not a whole number. So now we have to multiply this 1.5 by some whole number to be able to end up getting a whole number. So think to ourselves, what times 1.5 could get us to that whole number? 2. Very good. So if we multiply this 1.5 times 2, we would end up with exactly 3 moles of carbon. This is where we have to think like algebra. What we do to one thing, we have to do to everything. So we say 3 times 2, that gets us 6 moles of our hydrogen. And then 1 times 2, that is our 2 moles of oxygen. Okay. Now, our last part here that I'm going to write on the top here in pink is just writing down our empirical formula. So what we do is this. We just list the elements out in the order that they appear in the problem. And so we start with C. The subscript becomes that total mole there on the left, which is C3, H6O2. Okay? Questions? This is the empirical formula. We would go one step further for the molecular formula. Questions? Does anybody need this? Okay. All right. So last problem here. I'm going to go a little bit quicker over this stuff here because I need to emphasize, well, what's the difference between the empirical and molecular type of problems? And so we go through this. We have our acid. It's produced by lichens. Chemical analysis says it's 40.68% carbon, 5.08% hydrogen, and 54.24% oxygen. Now, what we have in this problem that we did not get before, the molar mass of the compound in the analysis. So now we got to go one step further, okay? So I'm going to go pretty quick here on this, and I am going to start out, and I am initially just going to say, okay, I don't deal with percent. They are automatically grams. I'm going to list them out in order here. I'm going to have 40.68 grams carbon. I'm going to have below that 5.08 grams of hydrogen. And then the last part here, I'm going to have 54.24 grams of oxygen. Now, these are the same substances, so they're going to have the same molar masses as the previous problem. So carbon, we're going to say, hey, it's going to get divided by its molar mass, which is 12.01 grams of our carbon. If I go ahead, I calculate that out, I get 40.68 divided by 12.01, rounding to 2 decimals. This is 3.39 moles of carbon. Hydrogen, same molar mass as the previous problem, 1.008 grams hydrogen to 1 mole hydrogen. So 5.08 divided by 1.008, and we get 5.04 moles H. Then we divide by 16 grams for the molar mass of oxygen. That is the exact molar mass for oxygen there. 54.24 divided by 16.00. And we get 3.39 moles of O for oxygen. Now, here's our weird step. We look at these numbers on the right. It's technically a tie, but what is the smallest number we see here on the right? 3.39. So, again, weird step, but you have to divide everything by this 3.39. So I just go ahead and say, hey, let's divide everything by 3.39. Well, that makes the top and bottom pretty easy because that gives us 1 mole of carbon. That gives us 1 mole of oxygen. And if we turn to our calculators here, we say, hey, 5.04 divided by 3.39, we get in our calculator 1.49. Now, you can be in the ballpark relative terms. That's going to be close enough to 1.5 moles. And so we have to do a similar thing to get everything as a whole number. What do we need to multiply by? Yep. So we end up, and we have to multiply by 2 so that we get 3 moles of H. But what we do to one thing, we have to do to everything else. So we would have to multiply by 2. That gives us 2 moles of our carbon. And then that gives us 2 moles of our O. Now at this point in time, and I'm going to write this below, right now our empirical formula can be found. Okay, empirical formula. We start out, I say carbon. What's going to be our little number below carbon? Okay, we have hydrogen. What's our little number there? 3. And how about oxygen? 2. Okay, so at this point in time, I'm just going to verbally talk through this. If we found the molar mass of C2H3O2, you could Google it to confirm what I'm going to say. But if we did that, I would say, hey, 12.01 times 2, 24.02, plus hydrogen is 1.008 times 3, plus 2 oxygen, 16 times 2, gives us a value, a molar mass here, of 59.04 grams per mole. Well, here is where this 118 is going to come into play, and that is this. If we take this 118, you always take the given mass in the problem, and you divide it by the molar mass in our formula. You're going to get something around a whole number. Okay, so if we take 118.1 divided by 59.04 grams per mole, relatively, what's that whole number there? 2. So what this means is that our empirical formula needs to be multiplied by 2 to find out what our molecular formula is. So here's how I do this just to show you. We have our empirical formula of C2H3O2. Because of the ratio of molar mass found to molar mass in our empirical formula, we have to multiply everything here by 2. So what happens is that our molecular formula becomes C4H6O4. Okay, so it's a multiple of that empirical formula, and this would be called our molecular formula. Questions? Okay, does anybody need this?